Hey everyone, this is Professor Ross, and in this video we're going to be talking about doing inference for the correlation coefficient and using a simulation-based approach to that inference. So let's take a look at some notes here. So inference for the correlation coefficient with a simulation-based approach. Our key learning objective is going to be use the logic of statistical decision making. So whenever we're doing inference, we kind of use the same logical approach. We set up hypotheses and test the hypotheses against the data we saw, or we calculate a confidence interval. And so we'll talk about doing a hypothesis test with the correlation coefficient. Why do we need inference here? Well, generally, our correlation coefficient is calculated from a sample of data. And so we don't want to only be able to talk about what's going on in our sample. We want to be able to talk about what's going on in a bigger population. That's exactly what inference is, taking results from a sample, making conclusions or claims about a broader population. So we're going to do hypothesis test. And what are the hypotheses? Well, we almost always have the same null hypothesis when we're testing a correlation. The null is the same as what we've talked about whenever we have two variables. And here we'll have two quantitative variables. And that null is that there's no association between those two variables. So we actually have a symbol for the population correlation, and it looks like a lowercase p, but this is actually a Greek letter R. So this is what's called rho. That's the Greek letter rho, and it just kind of looks like a cursive letter P, but it's actually R. The symbol for correlation of our sample is the English letter R. The symbol for the correlation in the population is the Greek letter R, rho. No association is that rho is zero, and we saw that when we talk about the strength of the relationship. If we get closer to zero, it's weaker. Well, if you have a zero correlation, that means that your relationship has that there is no relationship at all, that the two variables are not connected. And then typically we do a two-sided alternative that there is some kind of association. Rho is not zero. Sometimes we can do a one-tailed test as well and do a one-sided alternative that we think we're going to see a positive association or a negative association. What's our process? Good news, folks. It's the same process we've used all along for doing a simulation-based approach. It's the 3S strategy. We're going to calculate a statistic. That statistic is R, the correlation coefficient, from our sample. Then we'll simulate, and we need to model the null assumption somehow with our simulation. And the way that we're going to do that is with more shuffling. It's actually very similar to what we have seen with both two categorical variables and one categorical variable and a quantitative variable. We're going to take all of our pairs of values and we're going to just shuffle up the response values. So we're going to say, hey, look, if we're saying that there's no connection between these two variables, then these pairs that we have don't necessarily need to go together. We can just shuffle them up wherever and see what kind of correlation comes out. So that's how we simulate this no association claim. And we see what kinds of results we tend to see, what kinds of correlations we tend to see when we do the random shuffling that models the null hypothesis. And then we take a look at the strength of evidence. We measure a p-value. How likely was it to find a result like ours if the null was actually true? And that's how we'll interpret the p-value. Let's try this out with a set of data in the correlation regression applet. It's foot length and height. So one of the authors' statistics classes gathered data on how long their feet were and how tall they were, feet in centimeters and height in inches. And we can take a look at this and see if there's a correlation and see if it seems significantly different from zero. So there were 20 students. We're going to do the 3S approach. So I'm going to go ahead and pull up our applets here. And we're going to try out a new applet this time. It's called the correlation regression applet. And this is the only applet we'll use for this entire chapter, chapter 10. So here's the foot length and height data in there by default. You can see there's 20 pairs of data, and we've got a scatter plot. I encourage you to pause the video right now and try to think through the 4 things we want to interpret on a scatter plot. First, form, strength, direction, and unusual observations. Just a few comments on that. It's clearly linear form. We can get an oval around most of this data, and it seems to have a positive direction. That means the correlation we see should be positive here. For as far as strength goes, the correlation will help us measure that, but I'm thinking it's moderately strong relationship here. And unusual observations, I guess we have maybe one person here who had not that long of feet, but was pretty tall. That's actually something like me. I have kind of short feet for my height. Or someone here who was relatively small feet, but especially short. So they might be a little bit of unusual, but nothing too extreme here that we need to really be concerned about. So there's a lot of stuff you can do here. The thing we're looking at right now is the correlation coefficient. We'll get into a lot of the rest of these later in this unit. And there it is positive, and it is strong, right? It's getting closer to 1.0. It's well above the 0.5 kind of middle level correlation. So how do we do inference with this? This is the correlation R for these 20 people, but we want to say, can we make a claim or a conclusion about the correlation for, let's say, all the students that these 20 students might represent, all the students at their college, if that's a fair population to think about. And so we need the 3S approach. Here's our first S. Our statistic is R equals 0.711. Next S is simulate, and we need to show our shuffle options in order to bring the simulator up. And let's just try one. What we're going to do is shuffle once and shuffle the Y values. In other words, we'll leave the X's alone, but mix up all the heights here. And I'm going to go ahead and show the data here. Oh, I forgot. It always needs you to pick a statistic. I forgot to pick one. Let's pick correlation. Okay, so as I mentioned, it's left all the foot lengths alone, 32, 24, 29, that's the same, but it has shuffled up all the heights. That is representing this idea that the null hypothesis claim is that height and foot length don't have anything to do with each other. So I may as well shuffle up the heights because it's not connected to foot length. We can see that we did see a negative correlation, and you might be surprised thinking, hey, people with bigger feet, they don't tend to be shorter. Well, in our model of if there were really no connection between these two, it wouldn't be surprising to see some negative correlations and some positive correlations. If I try another one here, now I see oops, that's another negative one. There we go, close to 0, but positive. The main idea is that we want to find out what kind of trends should we expect in the long run if there truly is no correlation between these two. And so just shuffling a few at a time is kind of the long, slow way to do it. We want to shuffle a whole lot. Before we get there, I'm going to show you the plot quick. All that this does is it shows you how the dots could get mixed up if we're randomly shuffling the Y values. So I've got, how many total do I have here? 8 total shuffles. Let's go ahead and get at least 1,000 more here. You can go more than 1,000 if you want. If with larger data sets, if you start putting too many here, it can kind of bog down, but at least go to 1,000. Here's what we would predict if the null hypothesis were true. Not too surprising, right? Centered around a 0 correlation. If it's really true that there's no association between these values, then we would see 0 correlation most commonly. And then still, anything between maybe a negative 0.4 and a positive 0.4, pretty common kinds of correlations to see in a sample size this size if there's really no correlation present in the population. So how can we find out if our result was typical by what the null hypothesis would predict, or if it's different? That's what the count shuffles greater than interface is. It's the same as what we've seen in a lot of the other applets recently, and or excuse me, for the whole course, basically, we count our shuffles compared to our statistics. So here, I want to put my 0.711, and we want to see how did mine turn out compared to the rest of this. And we can see that almost none greater than. Now let me just note that we could do less than. You almost never want to choose the choice that fills in over the top of the hump here, red. Or we could do beyond if we were going to do a two-tailed test. And that's kind of the default one to say, I'm not expecting positive or negative. Let's just look to see if there's anything different from 0. And you can see that we have a very low p-value. So I have a p-value of 0.001, which means there's only a 0.1% chance of seeing a result like this correlation we saw. If it's true that in the population, there's no association that the correlation is actually 0 in the population, we'd almost never see a correlation this high in a sample. That's very strong evidence against the null hypothesis, which claims there's no association, which means that we reject that null hypothesis, that there's no association. It looks like there is an association between foot length and height. And that's not too surprising. Taller people, longer feet tend to go together. But that's an example of how we can do a hypothesis test in a simulation-based approach with correlation. You might be wondering about the theory-based approach to testing correlation, and we will talk more about that. It comes down to being the exact same thing as doing a test with another statistic that we'll get into in the upcoming lessons. So we can do a simulation-based approach with correlation like this to do inference with the correlation and decide about claims about the correlation in a population.